So today we are going to go over the process of DNA replication in prokaryotes. First off, let's look at this chromosome of double-stranded DNA. In prokaryotes, the chromosome is circular like this, but taking a closer look, it is still the normal DNA we know, which is a double helix. On our DNA, we have these components that are necessary for the replication process. I will explain each as we go through the steps. We have gyrase, helicase, single-stranded binding proteins, ligase, DNA polymerase I, DNA polymerase III, and RNA primase. So, we start off with the parent DNA strands that will be replicated into daughter DNA strands. DNA is composed of 4 nitrogenous bases, which are adenine, cytosine, guanine, and thymine, which are held together by hydrogen bonds on a backbone of phosphodiester bonds. In prokaryotes, there is a single origin of replication where there is a +1 region, which is a sequence that signifies where replication will begin, and on either side of the origin of replication, there is a replication fork. In this area, a gyrase binds to DNA, which prevents the supercoiling of the strand upstream of replication, while helicase unzips the strands by breaking the hydrogen bonds between the bases. To prevent the strands from recoiling behind the helicase, single-stranded binding proteins bind to each individual strand to prevent the recoiling of it. Running left to right, the top strand is 3' to 5', and the bottom strand is 5' to 3', anti-parallel to each other. RNA primase binds to the single-stranded DNA and adds an RNA primer, which is where DNA polymerase III will bind and start duplication. The top strand is the leading strand and replicates with DNA polymerase III alone and one long strand, while the bottom strand is the lagging strand and replicates in separate sections called Okazaki fragments. DNA polymerase I follows behind DNA polymerase III and replaces RNA primers with DNA. Then, the gaps left behind by these between the Okazaki fragments are sealed together by ligase. If we zoom out, this is what the replication process looks like on a larger scale. Now let's say that DNA polymerase I made a mistake and paired up bases incorrectly. There is an exonuclease function in DNA polymerase I that will notice this error and proofread the mistake. And DNA polymerase will back up and fix its mistake. But if it can no longer perform this function, then any mistakes made by DNA polymerase I will go unchecked and unfixed, which can cause mutations and changes in the genetic structure. Thank you, and this is a page of my works cited.